last little theory bit. So this was in the slides for the very first session that we had based on, well, the second session, I think, on loss functions. So just as a reminder of what we'd already done, and we saw some implementations of this in the previous session, and there's this method, the deep Ritz method, which I'm very fond of. It's a way of solving a simplest case, Poisson's equation, via a loss function, which has a different structure to a pins type loss function. So pins is normally a sum of squares. Whereas the loss function that appears in the Ritz method, I mean, what's going to happen is that your minimum is going to be a negative number pretty much always, unless your solution is zero, then it's zero. Okay, and you don't know this number beforehand, that makes things trickier. But the big advantage of considering this type of loss function is this equation here. Okay, there's no approximately equal to, there's no constant that appears. It's my loss function at some particular trial function minus its minimum is exactly equal to half my error in the H10 norm squared. Okay, this is a very, very attractive property, because what it means is that if I reduce my loss by a factor of a half with respect to its minimum, of course, that means that I'm reducing this error by a factor of a half as well. Okay. If you have, for example, a very poor choice of weights inside your loss model, it's loss function, so if you have different terms and you weight them incorrectly, then what could happen is you could reduce your loss by a factor of 10, but your solution in the error or in the norm that you're interested in barely changes at all. And these kinds of things happen. So this is a very, very attractive equality. So one thing that we mentioned is that because we don't have this sum of squares structure, integration becomes a really big problem. Okay, you have to take a lot of care when integrating. If you use a deterministic fixed integration rule, then your approximation of the loss ends up far, far lower than its theoretical minimum, which can only happen if you integrate poorly. Right? It's not just that you can have integration errors, it's that it favors integration errors, which is kind of different from the case of pins. You can still have overfitting in pins, but you don't necessarily gain as much as you can. You can never go lower than zero, right? But in this case, you can get lower than the minimum by integrating poorly. Right? Now, these features tend to be quite common in other methods based on weak formulations of PDEs. Okay, so the pins formulation is based on the strong formulation, whereas weak formulations are based typically, if we think we can go to a slightly different PDE. So this could be the weak equation that we're interested in. And this is, for the most part, the equation that I'm personally interested in when I'm doing these kinds of methods. So what's the equation we have here? We can understand this sigma could be something like a resistivity. And we're looking for essentially solutions of the transmission problems of Poisson with variable coefficients that satisfy this equation. So I want a U such that sigma gradient U dot gradient B plus FB is equal to 0 for every possible test function B. Now, when these guys are discontinuous, in principle, you can't use a pins formulation, because what happens is you have low regularity solutions. They're not twice differentiable, so the pins loss doesn't really make sense. I mean, it's not correctly posed. Now, this type of problem lends itself basically to the same Ritz method. I mean, more or less, this is the same functional that we had in the case of just regular Poisson's equation, where the sigma was equal to 1. But we now just have this factor here. Okay? Now, this loss function, if we use it, satisfies basically the same kind of equality. So the distance to my minimum of my loss is equal to this guy here, which corresponds to what we would call the energy norm of the solution. That's the energy norm, and it's directly linked to the PDE that we want to solve. So once again, even in these problems where we don't have a strong formulation because we don't have sufficiently smooth solutions, this method can still work to give us solutions. And in particular, we have this very, very, very attractive property where if we reduce our loss, we know that we are reducing our error, okay? Modulo integration errors and so on and so forth. Okay? So there are many problems where the weak formulation is more natural, it might be more useful, and there are many situations where it's the only thing that we can do, because it might be something like this where the strong formulation just doesn't hold. So what we need are some techniques for trying to do things involving weak formulations. And in a more general sense, because the Ritz method has a very limited domain of applicability, right? It only works essentially if you have an elliptic positive definite symmetric PDE, which of course isn't every PDE. If you have even like the Helmholtz equation with a sufficiently large frequency that isn't very large, then this method won't work. Okay? So we need other methods to deal with weak formulations of PDEs. Now, everything I'm going to say is in the context of elliptic equations, basically, but a lot of the ideas can translate into other PDEs. Okay, but I think these are much simpler to explain the ideas. We have to talk a little bit about functional analysis. I'll try to keep things very, very light, but the whole idea is that we're going to have some abstract formulation. We're going to be thinking that we're looking for solutions in some Hilbert space. And we have its dual space, which is all of this continuous linear functionals that we have on our trial space. Okay? So I'm guessing you guys are all physicists. You probably know plenty about this, right? So on our dual space, so what we have is there is an induced dual norm. So we have a norm on our Hilbert space, and we define over the dual space a norm, which is given by a kind of maximization principle. Okay. We look at, given an input which has got norm 1, essentially, how big can my output of my functional be? Now we can think of our PDE, and this is the kind of abstract setting of how we can understand a PDE. We think of a linear operator. Again, I'm just thinking about linear equations to make life easy. We have a linear operator that goes from our Hilbert space, which I'm taking to be H1 in this particular case, into its dual. Okay, so this linear operator, we think we put in our candidate solution for the PDE. Then we get something which is in the dual space. How does it act on things in H1? Well, by this kind of integral. This is the kind of thing we had in the definition of the weak formulation. Then we have some element of the dual space, which corresponds essentially to our right-hand side. Okay, we take some test function, we integrate it against F. So understanding this linear operator from our trial space to our test space, we just say that this operator gives us a particular thing in the dual space. Okay? Now, for this problem, at the very least, you can choose, and there's various equivalent norms that you can choose for these kinds of problems. And if you choose the equivalent norms correctly, then essentially by a kind of Pythagoras type theorem, what you can say is that my error in H1, so I'm thinking of the case where I have a Dirichlet condition, but I don't impose it strictly. Okay, so I can put anything in H1 into my problem. Then my error in H1 is going to be equal to the dual norm of this residual, where the dual is taken over the trial space, plus this horrible H half norm, which exists on the boundary. Okay. So this is, again, exact. You have an equality here. So if we want to solve this problem with a homogeneous Dirichlet boundary condition, I can decide, okay, do I want to try and evaluate this guy? I'm going to say no, because fractional Sobolev norms are not fun to play with. They just introduce problems. So I'm going to be thinking of the case where we have pinning. Okay, we forced our boundary condition into our neural network. If we didn't do this, then we could consider a loss function of this form, which then becomes very, very natural in the sense that we have this very desirable relationship between the loss that we want to minimize and the error in the norm that we're interested in. Again, I'll just repeat, this part is just too complicated and I really, really don't want to touch it. So I'll use pinning, and now I just have to deal with this dual norm that we have here. Now, this still isn't easy, right? Okay, fractional Sobolev norms, these are horrible, but dual norm, okay, so we can get rid of them. The dual norm is still complicated, but at the very least, we have some techniques that have been studied to try and work out how to evaluate this guy or approximate it in some sense. So one of the approaches is to think, okay, we want to estimate the dual norm of this guy. But the problem is BU minus L, this is something which lives in the dual space. And in principle, we can only access this guy by making it act on test functions. Okay, I mean, we can't assign it pointwise values, for example. And we could, but this is solving a PDE itself at the same time, right? So we have this duality pairing. We say, okay, given some trial function, I can act on a test function. And now if both are fixed, this is something that in principle I can evaluate. Okay, this just turns into doing some derivatives, doing some integration, and life is good. Now, one of the first methods to consider, or at least as far as I'm aware, to consider trying to do weak formulations was the idea of V-pins, which is variational physics-informed neural networks. And essentially what they say is, let's just take a set of test functions and do this duality pairing over some user-prescribed fixed set of test functions. We evaluate this residual acting on the test function, we square it, and we sum over all of them. Okay? So you specify what these test functions are. You can take them to be piecewise polynomials, splines, and whatever you like, right? But the thing is, I mean, the loss is very, very sensitive to the choice of test functions that you make here, right? And in fact, in the original, or at least as far as I'm aware, the original work based on using V-pins, what they ended up doing actually wasn't based on weak formulation. If you sort of look carefully at the kind of calculations that they did, their choice of test functions means that if you took an appropriate limit when this, you can only do this for finitely many guys, if you take this limit, you don't get this kind of relationship. What you would get is that this guy turns out to be equal to the L2 norm of the strong residual, okay? Because they chose their test functions. Maybe it's strong to say incorrectly, but not in a way that's consistent with the H1 error. They did it in a way which is consistent somehow with the pins formulation. But this is much harder to evaluate because you're no longer doing one integral. You're doing an integral for every single test function. If you have a very rich test space, this means you have to be able to have very oscillatory solutions, which means integration is harder, and so on and so forth, right? So in this original work, which I've cited here, I mean, really, their formulation is just a really complicated method, which is mathematically equivalent to doing pins. Okay? And even within this, what you could do is say, okay, what we're doing is we're approximating some finite dimensional subspace of the dual space. But if you change your basis, you're changing the loss function. Right? So again, it's not just the space that it's generating that you have to be careful with, but also the basis that you choose for your space, which can change the kind of solutions that you get. And it can completely break this relationship here. Okay, we ignore this guy, and this is the guy you want to preserve. So there's been a series of works on what were later called RV pins, robust variational physics-informed neural networks. And the idea is essentially, well, if we choose the test functions, so these VK that we have here, to be orthonormal in H10, then what you have is essentially that this dual norm, which is the guy that we want to evaluate, this is basically equal to this thing which we can calculate and some truncation error. Okay? If we think, just to try and make things very, very concrete, if we're on something like 0 to pi with periodic boundary conditions, we could take complex exponentials. Right? And then essentially, I mean, morally, this guy becomes like a truncated Fourier series, more or less. So, okay, so you have some truncation error, which corresponds to the high frequency components that you haven't touched. But at the very least, you should be capturing the low frequency components of your residue. Now, if you don't take this orthonormality condition, if you take the same subspace, which is generated by the test functions that you choose, but you choose a different basis so that they're not orthonormal, and you take a loss which looks something like this, then what you have is that you still have a kind of can be controlled by, but the constants that appear when you compare these guys are huge, right? You might have that the dual norm is somewhere between 10 to the minus 3 and 10 to the 3 times this guy. I mean, but if you have a very ill-conditioned basis, then the correspondence between this guy and this guy gets very, very weak. Okay? Then what's the other problem that we have here? I mean, we need to use this method correctly. We need an orthonormal basis for our test function space. This is a difficult problem in itself, right? I mean, a very, very natural choice of orthonormal basis for H10, which is somehow very much in line with our intuition of thinking of truncating a Fourier series, would be to take your basis functions as the first k eigenvectors of the Laplacian. Somehow this is almost the most natural choice. Now, finding the first k, where k is large, eigenvectors of the Laplacian, this is probably harder than the PDE you wanted to start with. Okay? So in some very, very basic cases, you have these guys available, but in a very complex geometry or something like that, I mean, this could be a very, finding the basis functions themselves could be harder than the problem you actually want to solve. But nonetheless, in some very simple geometries, we know what these eigenvectors of the Laplacian are, and they have simple representations, so we can see what happens when we use this idea. Okay? So if we're in 0, 1, or 0 pi, sorry, then our eigenvectors of the Laplacian with the Dirichlet boundary conditions are just sine kx over k with some multiplicative constant there. Okay? This is easy enough to work out. This is easy enough to implement. We don't have to do any calculations, right? One thing to add, you can easily extend this to n cubes by doing sort of tensor products of sines, right? Sine kx, sine k2y, etc., etc. Okay? Right. So this is the kind of result that we get if we do this idea of using these trigonometric basis functions, which we know to be H10 orthogonal, in this V-pins framework. So okay, I have a really, really simple solution. I have a very good approximation of it. I can see my loss as it's evolving. Okay, it's going down, but it's the loss, it should be going down. But the most attractive feature is this guy on the right. So what I did is that at every iteration, I measure my loss, and I also measure my error in H1. So I do 1 point, I have loss on the bottom, H1 error on the left. And what we see is a very, very good correlation between the two. This is this very desirable property. I know that if I reduce my loss by a factor of a half, I'm reducing my error by a factor of a half, which doesn't always happen with other formulations. Now, one thing to have in mind, I mentioned this comment that you need to be careful with the test functions that you choose. Okay, so in this case, I take exactly the same basis functions, but I now multiply them by a random number. Okay, I think it was between 0.1 and 10 or something like that. So my test function space hasn't changed, right? This is still a basis for the same subspace H1. But effectively, all I've done, if we go here, is introduce some weights in this part here. And this breaks the relationship between the loss that I'm evaluating and the dual norm that I really want to estimate. And what we see here, we kind of break this linear regime around here. Okay, then it goes back to linear afterwards. But if I take a much larger range of these weights, then what we would see is further and further and further breaking of this relationship. Then what some people had proposed at one point was to just use essentially finite element basis functions, but just using them in their local representation. And in this case, what's going to happen is essentially you get a huge condition number, and this relationship, you end up, and basically the two aren't at all related anymore. Okay? So not choosing correctly, even if you have the right space, choosing the right basis changes the results that you have. And another thing to bear in mind is that we can think of this summation over our basis functions, and this is almost like integration. If we think back to just the case of Fourier, if we think we're testing against complex exponentials, now we get the Fourier transform in some sense of our residual. Now our loss is the integral of the Fourier transform squared. Now this is an integral in some sense on its own. If we use fixed basis functions, this is kind of like doing integration over a fixed grid. We can get overfitting. Okay? And this is more or less what we see in this particular example. So The solution isn't too bad, but in this case, I only take 5 sine functions for my basis functions. So my loss is going down. I end up with a loss of the order of 10 to the 6, 10 to the 7, more or less. But what we see is that after a certain point, I have completely broken this linear relationship between my loss and my error. And I really interpret this picture as overfitting in Fourier space rather than in real space. So once we get down to this point, by the time my loss is around 10 to the minus 3, I've now reduced my loss by 4 orders of magnitude. And my error, okay, it's not changed a huge amount, but it's going up. Not a huge amount, but it's going up. Yeah. So you have to be really, really careful with the kind of test functions that you're employing if you're doing a VPINs framework, because you have all of these issues that are here behind. Another thing which makes things very, very complicated is that the test functions, as I said, they're difficult to evaluate. So if you want something like the eigenvectors of the Laplacian, this problem isn't trivial. If you're solving elliptic PDE, this is harder. Right? But another problem is that if you're in higher dimensions, you get a sort of curse of dimensionality, which you can see just by thinking of this cube example. My eigenvectors of the Laplacian are like sine k1x times sine k2y plus sine k3z, and so on and so forth. If I want to capture 10 wavelengths in each direction, now I need 10 to the power of dimensions. Right? So this is a curse of dimensionality in the test function space, just like how integration has a curse of dimensionality in real space. So this becomes complicated in higher dimensions, and as well, the test functions must naturally be highly oscillatory. Again, we think somehow the natural choice are eigenvectors of the Laplacian, but the higher the eigenvalue, the more oscillatory it is, and the more oscillatory my eigenvector is, the harder it is to integrate. And then we come back to this issue that it's really difficult to integrate neural networks, and so it's hard to integrate neural networks, and more oscillatory it is. Opposite. And in weak formulations, you have a much higher sensitivity to integration errors. So if you're putting something hard to integrate into your PD, into your loss function, and you have sensitivity to integration errors, there's going to be a problem. So one method which tries to sort of overcome all of these issues about how to correctly choose the test space and so on and so forth is to just try to do everything with one very, very carefully chosen test function. Okay. So this is the approach of weak adversarial neural networks. So if you're familiar with adversarial neural networks in the typical situations, generative networks, it's based on a very, very similar idea, but in the context of PDEs rather than data science. So what we can recall, so the thing that we want to evaluate is going to be this dual norm, which for the particular problem that I have, this is a very, very good representation of the error of my solution. This is defined by a kind of maximization principle. Okay, I just maximize the action of my residual on the test space divided by the norm. So if I want to minimize this over U, now I have a min-max. Right? So the idea is that we have a min-max problem where now I have one U. This is my trial function, which will be the solution to my PDE. Then I have a maximization, which is used to try to evaluate the dual norm. Now, if you have a positive definite symmetric problem, you shouldn't be using this approach. Okay, I'm going to show it for a positive definite symmetric problem because it's just easier to show the ideas. But if you have a positive definite symmetric problem, the unique maximizer of this is U itself. And then you basically end up with the Diepritz method. Okay? So this doesn't make sense for symmetric positive definite problems. But if you have something like, for example, Helmholtz or something that isn't symmetric, you have some kind of advection term, then this gives you a way to handle weak formulations without using the structure of the Diepritz method. And it's worth mentioning the same holds for these VPINs methods, right? The only thing they're really doing is just evaluating the dual norm. So if your dual norm corresponds to your error, then it can be an appropriate method. So the idea of Wang's weakly adversarial neural networks is that now instead of just training one neural network to be our solution, we train two neural networks. we have this optimal test function, optimal in the sense that it solves this maximization problem. And then we do a min-max over these two networks, the test function and the trial function. So again, this can be done in principle using gradient descent on our U and a gradient ascent on V. Now, this is one of the cases where the black box functionality of TensorFlow makes things a little bit more complicated. TensorFlow can only really minimize or maximize. If you want to minimize with respect to some variables and maximize with respect to others, you have to do some part of the training loop by hand. As I say, this is based on weak formulations. We don't have a kind of sum of squares type representation of our loss, so this becomes quite sensitive to integration issues as well. But at least one thing that it avoids is, in principle, if we do well this maximization problem, we avoid this problem of overfitting in Fourier space because we're always choosing the best V. And as well, one benefit here is that if we have a relatively smooth solution, or but probably better to say a relatively smooth error in our solution, then the optimal V has very similar regularity because it solves a very similar PDE. So rather than introducing sine 500x, which now we have to integrate, which becomes a whole problem, what we hope at least is that because V is going to be the solution effectively of some PDE, it should have higher regularity and it shouldn't be much worse behaved than the U itself. And this all depends on the exact problem that you have. And in the case of a positive definite symmetric problem, the optimum V is precisely your error. Okay, so it has exactly the same regularity as the error because it is the error. Of course, this is not without problems. One of the other big problems is that min-max problems are harder, okay, both analytically, both in terms of implementation. Okay, they're a lot more sensitive. The theory is not nearly as well developed. So this can be very unstable when you do a training process. But to see the idea, again, this is actually a positive definite symmetric problem, so it doesn't really make sense to be using WANs here because we know what the maximizer is. But nonetheless, we can see how this works. So I go back to the same problem I had before. Here's my solution. Things look nice. Here's my loss, doing more or less what we expect my loss to be doing. And again, we have this comparison between the loss and the H1 error, and it's following this very, very nice linear relationship. The two are proportional, which is what we expect to be happening. But this comes with a very, very big caveat. To get these pictures, I had to do a lot of fine tuning. Here I was changing the optimizers, and in reality, when you do this min-max, you don't want to do one step of U, one step of V with basically the same optimizer. You might want to do 10 updates of V, then one update of U, where with U, you use a much smaller learning rate and things like this. And it's not very, very clear how these optimization problems should be implemented. So after doing loads and loads of different attempts on trying to get this thing work, I got something that worked. But on the next slide, which we have here, this is what happens when this was the first attempt, I think, that I did in trying to implement this example. So in this case, I think if I remember rightly, it was just one step of each with the same optimizer. Then what happens is things go well up to a certain point. I get my loss and error are more or less in agreement until my loss is of the order of 10 to the minus 1. Then what happens? My loss reduces by 12 orders of magnitude with absolutely no improvement on my solution. Okay? So what's really happened here, and you can see in the loss as well, and you think that sort of looks like it should be looking, and you can tell something's going wrong here. My loss is fluctuating again over, this isn't monotonic, right? It's going over 12 orders of magnitude in oscillation. So essentially what happened here during this training process, if we go back to this min-max, is I got a reasonable solution, essentially, which is why it doesn't actually look too bad, even though I've lost my relationship here. Then this solution V basically goes to 0. Now, once it goes to 0, whatever I have here, I'm going to get 0. Right? And then what that means is that my U is basically doing nothing. There's no gradients there. The U stops updating. The V stops doing anything useful. And I have however many thousands of iterations. Oh, sorry, it's this one. Where basically everything is broken. So this is quite an unstable training method, but I mean, when it works, this is something that can be useful when you have weak formulations without having to have these problems about knowing what the test function space is. So just some concluding remarks on the weak formulations themselves. Okay, so sometimes these are the only options that we have because I mean, we're not always interested in high regularity PDEs. Sometimes the natural formulation of our problem is a weak formulation and we can't do anything else. Trying to work out how to define an appropriate loss function becomes quite a bit more complicated. Even in the case of strong formulations, the mathematical framework behind it is sometimes somewhere between weak and unfounded, but at the very least you can write things and you know that more or less they should work. But things tend to be much more sensitive when we're talking about weak formulations, and you need to think quite carefully about what kind of norm am I trying to approximate? Is my loss somehow representative of the error that I'm interested in? And one thing that comes up quite a lot when we're dealing with weak formulations is that integrals can become far more challenging. I mean, Pins type approaches based on strong formulations are sums of squares. You can't really hope for anything better when you're doing optimization. But once we're in the world of weak formulations, we lose that structure, and that makes things very, very sensitive to integration. Okay. So I think that's everything that I wanted to say on weak formulations. If there's questions or comments about. I get one final comment on that, I guess, is that everything that I've said about these relationships, this is based on very, very particular elliptic equations where you know that you have this kind of relationship. This will all depend on your PDE. You have something nonlinear, okay, but different story. You have some kind of wave equation, different story. But in the cases where you have this, you have all of these methods and problems with you. Okay. Okay. So in that case, get that open. So one thing that I designed just to finish off the course, essentially, so I have in the GitHub on session 3, it should be, yep, session 3, what I've just called a problem sheet, okay? So, because I've sort of picked up that there are various people with various levels of experience in using neural networks or for PDEs or for other applications. And so the idea is that this isn't a problem sheet in the sense of you need to do this, and then you need to do this, and you need to do this. And really what it is I've given you code with some particular problem. For the people that want to get a bit more experience, I mean, this code gives you a good enough backbone to start playing. Okay? So the way that this sheet is organized, I mean, it's all very much, here are the things you can play with, what kind of things that you can consider. And I think it also serves just to go through this piece by piece and we can discuss this. It gives us a way to sort of consolidate all the things that we've seen in the course as well. Okay. So if you want to decide to have a try and play with the code that we have here, I mean, the very first thing that you need to kind of decide is what kind of architecture you want to be considering. And the initialization, this is a big part of your problem. I mean, you can choose how to initialize your weights, you can choose how to initialize your biases, you can do things stochastically, you can manually say, I want all of them to be 0.5. And all of these things are going to completely change the way that you train. Maybe you start with a very good solution and you converge very quickly. Maybe you start with basically a constant solution and it doesn't train after 10,000 iterations. Or you start with something that's got so many jumps in the derivative or whatever that it becomes very unstable and blows up in 2 or 3 iterations. This can all be seen just by changing the initialization. But as well, you have various activation functions. And you have the hyperbolic tangent, which tends to be the one of choice in the world of PDEs. But there's other ones that exist within TensorFlow, but you can also put any function that you like as an activation function. And this sirens initialization, which uses sign activation functions and is morally like a Fourier transform or a Fourier ansatz. And this is quite useful. But given that you can put basically any function that you like as an activation function, and if you try with something like exponentials or ReLUs in the context of PDE type problems, you'll see very quickly that things don't work. And these can be fun little experiments to try and work out why things are going so bad. And yes, one thing to emphasize here, I mean, the initializations that you have, these are somehow related to the activation functions that you have. I mean, so I mentioned there's this glorot initialization, which is the default one. If you don't touch anything, you just say, give me a dense layer. This is a particular initialization where your biases are 0 and your weights are taken according to a uniform distribution. This is all based around the hyperbolic tangent activation function. And there's a theory behind why this should be good. In reality, it doesn't depend too much on it being tangent, but it depends on having your activation function being 0 at 0 and differentiable. Or differentiable with derivative equal to 1. Now, the sigmoid function, which is kind of similar, right? I mean, it still goes like this and then has a transition and goes up in the other way. But the sigmoid function, the difference is at 0, it's equal to 1. You change the initialization, or use the same initialization for the affine maps, but you change the activation function, then all of this theory of why it works with a hyperbolic tangent goes out the window. Just the sort of up to leading order behavior of your activation function is different. Okay. One thing that I often find quite instructive is once I define some kind of architecture, at least defining a low-dimensional problem where I can plot things, I just plot what it looks like when I've initialized it. If the whole thing is constant, then I know more or less that this is going to be really, really bad. If I have some ridiculously high gradients that are appearing somewhere, then I can guess this is probably going to be quite unstable. And you can already sort of see with your own eyes whether an initialization is giving you the kind of features that you want to see in your solution. So you must know something about what your solution should be. And just by looking at the initialization, you can see how these things work. And the two big things, once you've decided if you're going to use at least a feed-forward network, once you have the kind of activation function you want to consider, you need to make a decision on how big you want your network to be. You can either put lots and lots of neurons, or you can make it very, very deep. And these things are going to affect your performance. These things are also affected by the way you initialize all of your weights. And all of these things are completely interconnected, and changing one might mean you have to change all the other to try and get good results. So within this code, I mean, I've used a stratified Monte Carlo in order to try and do the integrals that correspond to the problems we want to solve. But I mean, there's all kinds of different quadrature rules that exist. Some of them are stochastic, some of them are deterministic. You have some quasi-Monte Carlo methods like Sobel points, which you may or may not be familiar with. You can consider just classical Gauss rules based on deterministic fixed integration meshes. And all of these things can really, really change how you converge or how well you converge or if you converge in the extreme cases. So these are all things to be careful of. Now, for a lot of the problems that I've shown, I think almost all of the problems that I've shown, I've taken really simple forcing terms, really smooth, really nice, not very many features. But I mean, all of these issues, how do I initialize correctly and so on and so forth, these can change quite significantly depending on the type of right-hand side you have, because this is dictating what your solution should look like. This is dictating, if you have a very oscillatory right-hand side, you probably have a very oscillatory residual. So this can now affect the optimizer as well. And in the kind of the typical cases, and whenever we're trying out some kind of new method, so okay, the first thing we try, we do the simplest right-hand side that we can possibly think of just to see if it works on a smooth solution. If it doesn't work on a smooth solution, it's not going to work in anything interesting. Then you have a go, you say, okay, what if I have a very oscillatory solution that's still smooth? Or what if I have something which is going to introduce some kind of discontinuity into my solution, or discontinuity in its derivative or in its second derivative, and so on and so forth. If I have some kind of appropriate singularity in my right-hand side that forces a singularity in my solution, how do I need to be changing my architecture, my loss, my optimizer, so on and so forth to try and capture this behavior better? And changing just one little bit on the right-hand side, you might think these methods will always work for Poisson's equations. No, it will work for Poisson's equation with the right-hand side you've chosen. You change the solution, you need to change everything. When we have boundary conditions imposed, I mean, there's all kinds of different ways that you can do this. If you're working with something like the deep Ritz methods, then you have a differentiation between natural and essential boundary conditions. The natural ones live in the function space. This would be something like a Dirichlet condition, but then a natural boundary condition would be something like a Neumann condition, which comes from the solution, or the minimizer will satisfy this. Okay? So if I have some kind of problem like this, well, I can either introduce some kind of pins formulation where I now have to have a term involving the derivative in my loss, or I could use some weak formulation that automatically sticks it into the solution. Even in the simplest case of a Dirichlet condition, what I can do is I can try to pin, I can change the cutoff function I use for pinning. Right? In all of the cases, I've used something like x1 minus x. I could happily choose something which is like just goes up, flat, and back down again. All of this is going to change the behavior of your training process. And you can also introduce penalty terms. Once you introduce penalty terms, you enter into the world of the correct norms for boundary function values. This is a whole thing in itself. Once you have different components of your loss, you have to decide how to weight these things. Again, whilst I've only been looking at really simple scalar PDEs, if you have a coupled system, well, your loss is going to have essentially two components, one corresponding to one PDE, one corresponding to the other. And all of these issues that I said about weighting on boundary spaces, now you have to think about how to weight the different components of your loss because they do different things. And part of this can be informed by having some functional and analytical framework that tells you this constant should be something like the Poincare constant. This kind of analysis you can sometimes do. But then again, in practice, it might even be contrary to what the theory is telling you would be the correct or natural choice. So all of these things need to be taken into account. If you really want to push the code to its limits, I mean, all the stuff that I've put in GitHub, and you can easily adapt a lot of it to a lot of strange other problems as well. I've only really used, well, I've only used linear PDEs, or linear ODEs even for the most part, but changing all of this code into nonlinear PDEs, this just means changing the way you define your loss. You just do the arithmetic. Now you have something like u squared, u cubed, whatever. I mean, it's all exactly the same framework. And it's not like trying to use finite elements for nonlinear problems, where the linear problem is one story and then the nonlinear story is another. We've started with something horrifically nonlinear, so there's no harm in making it just a little bit more nonlinear. And I've mentioned this really simple toy inverse problem. But I mean, this is an approach where you can invent all kinds of problems. And then maybe in research, you have real problems you want to solve. If you just want to play with the code, then you can invent all kinds of problems. I mean, I've phrased a lot of these in terms of inverse problems. I have some measurements. What I want to have is identify some kind of toy material parameter based on the measurements, knowing that my guy satisfies a PDE or an ODE. But exactly the same language mathematically can be used to interpret a design problem. I may have some coefficient inside my material or inside my PDE, and I want my solution to have a certain property. Again, I can do more or less the same thing. If I want my solution to be as big as possible at a given point, I could do the same framework. I allow this extra parameter that I want to optimize over to be optimized over, and stick something else in my loss that says, make this guy big. This is very, very versatile. It's very flexible. Whether it works or not is always a different story, but you can always put something in and see if these guys work. And going to higher dimensions, I mean, I've only really talked about 1D problems with a couple of 2D problems. And this is only just because then I can show lots of nice pictures. I mean, there's absolutely no harm, especially in the pins type points of view. And I have one example. We're solving like a 5-dimensional Poisson's equation on the ball. I chose the ball because you can do Monte Carlo sampling really easily. And it's no harder to implement within this framework than solving a 1D Poisson equation. The only hard bit is sampling. Everything else is just as easy. And there's no real complications going on. Again, with the big caveat that this is all in principle, actually getting your hands dirty and getting the thing to work. This requires far more care and a lot of trial and error because unfortunately there's not a lot of theory behind it. Okay. So I think with this, and this is kind of the kind of things that we can sit and play around with. I think this has been a nice summary of all of the kind of things to think about when you're playing with neural networks. And I guess we could, if you have questions or comments or other doubts, we can just play. I mean, in principle, I mean, you can do everything. And then, I mean, I know people work on it, but I mean, because I don't do stuff with hyperbolic equations, I'm not very sure on the details on how these things work. But I mean, yeah, in principle, if you have and some of the issues come down, this is not to do with things to do with wave propagation. There's issues around boundary condition, how to do things like a perfectly matched layer with a neural network. I understand to be really complicated. Can't tell you more than that, but I know that it's much more complicated. There is one very hand-wavy argument that makes me think that in a sense, like wave equations are easier than heat equations. And somehow the reason is because you have this time reversibility, right? Whereas the heat equation isn't. So if you try to use a neural network, which now has time and space, if you have time reversibility, somehow it tells you that you're not forming at zero much more of a singularity than you have on either side. But with the heat equation, if you have even something like a smooth function, then you have a really, really smooth function for positive time and maybe no solution for negative time. So then it becomes hard to solve because as you approach the initial condition, you think backwards, you're approximating a singularity, which the neural network struggles to do. But time reversibility in some sense, I think, is easier in that respect. I mean, if you have some boundary conditions, if you have a PDE, then there's no reason why, in principle, you can't try something. But having the correct loss functions and things like that in order to make sure you have a good representation of your error, and that's something that I'm not very aware of, but I'm certain someone must have done. Thank you.